Electricity is one of those things we take for granted. We all know what to do with it. Plug this in, plug that in. Oh, we're very good at plugging things in. But it takes a power failure to make us realize how utterly helpless we are without it. The basic principles that led to the development of electrical generators began with the discovery by Hans Christian Ørsted in 1819 that a magnetic field results whenever there's a flow of charge through a conductor. 10 years later, in 1830, the possibility that a magnetic field could generate a current in a conductor became a reality. Working independently, American physicist Joseph Henry and British scientist Michael Faraday performed similar experiments and arrived at the same conclusions. However, since Faraday published his results first, he is credited with the discovery of the effect which is now called electromagnetic induction. Faraday's experiment involved an iron ring and two coils of insulated wire. The primary coil is connected to a battery, and the secondary coil to a galvanometer. A galvanometer registers minute current flow through a conductor, with its needle also indicating the direction of the current flow. Faraday observed that the instant the primary coil was connected to the battery, the galvanometer registered a brief pulse of current in the secondary coil. But, much to his surprise, the needle quickly returned to zero, indicating that all current flow had stopped. However, when the primary coil was disconnected, current was again briefly generated in the secondary coil. Only this time the flow was in the opposite direction. Changing the current in the primary coil somehow induced a current in the secondary coil. Faraday recognized that connecting the primary coil to the battery causes a magnetic field to build up within the iron ring. As the field grows within the ring, it induces a current to flow through the secondary coil. Once the field in the ring is at full strength, it is no longer changing within the secondary coil. The result? No more current in the secondary coil. When the primary coil is disconnected, the magnetic field it produced collapses. As the field in the ring collapses, it again induces a current in the secondary coil, this time in the opposite direction. Faraday's apparatus would today be called a transformer. Experimenting further, he found that the same results were obtained using a bar magnet instead of the primary coil and ring apparatus. One of the most important conclusions from Faraday's experiments can be stated this way. As long as the magnetic field within the coil is changing, a current will be induced in that coil. This principle was used by French inventor Hippolyte Pixii in 1832 to develop the first electric generator. Although it was clear that induced current flowed in different directions, depending on whether a magnetic field was growing or collapsing, why it was doing this was a mystery. 2 years later, German physicist Heinrich Lenz provided the answer. He realized that the induced current generated its own magnetic field. But even more important, Lenz discovered that the induced magnetic field is always opposed to the change in the external magnetic field that caused it in the first place. As the south pole of the bar magnet approaches the coil, a south pole is induced at the near end of the coil. Opposing the forward motion of the bar magnet. The beauty of Lenz's discovery, now known as Lenz's law, is that we can identify both poles of the induced field. And we can use the left-hand rule for coils to determine the direction of the induced current. Remember that the thumb points toward the North Pole and the fingers curl in the direction of current flow. Once the bar magnet stops moving, the field is no longer changing, so there will be no induced current, and therefore no magnetic field. In other words, everything in the coil stops. Now, suppose we begin moving the bar magnet away. Once again, current flows, and a magnetic field is induced which opposes the movement, this time by establishing a north pole at the near end of the coil. The left-hand rule for coils shows that the current flows in the other direction. The principles developed by Faraday and Lenz are applied today in the generation of electricity. The pressure of water or steam is used to turn a turbine connected to a generator. In its simplest form, a generator is an armature consisting of a coil of wire around an iron core, rotating within a magnetic field. The movement of the armature through the magnetic field induces a current in the coil. And according to Heinrich Lenz, the induced current will produce a magnetic field in the armature with its own north and south pole. This field will oppose the armature's movement through the external magnetic field. From here to here, this end of the armature will be a north pole. So at the top, as the armature is turned, this attraction opposes movement away from the south pole, and this repulsion opposes movement toward the North Pole. As the armature rotates just past the external poles, the induced current and magnetic field reverse, opposing movement through the second half of the rotation. Again, the induced current and magnetic field reverse as the armature passes by the external poles. Since the direction of the current reverses every half rotation, the resulting flow of charge is referred to as alternating current. And the principle of electromagnetic induction is used in giant electric generators, which supply enough alternating current to keep us tuned in and turned on.